axis. The corresponding axis part seems like sort of arbitrary. I don't really get.
Okay,
what
yes.
they're asking.
I think that's vestigial from how I used to make you draw sometimes stress cubes in funny rotations,
Okay.
but it's just too hard to do. So I took all those out, and so I left.
Sure.
Yeah.
Because I was just like, it's like, okay, that one's X and that one's Y. And
Yeah.
I'm just kind of like, no.
Yeah, I think
I was just drawing
that's why those are there.
just drawing a coordinate system like as best I can to the eigenvectors.
Because I used to have things where I would make you try to rotate it 30 degrees and then draw the cube rotated that way. But it's just hard to draw and hard to visualize.
Vestigial word of the day.
Yeah, right. Like our vestigial tails.
Yeah. Or like those bones that whales have.
Uh-huh.
They're just
Yeah.
like island of bone.
Yeah. Right.
Yeah, totally.
Okay. Any other homework questions? Okay.
Where'd you make it take so long?
Yeah.
The tension and compression part took me like 3 hours.
That sucks.
Same.
What an a-hole.
Yeah, well, and some of those, one thing I was wondering, it's like, so some of those you could just do one pin and that was enough, but some of them you actually had to do like the moments. and
Yeah.
everything, it seems like.
Yeah, that one had a million elements in it.
Yeah.
But I mean, I'll tell you, for the people who took statics from me, you'd sure rather do that as a truss than do it as a full collection of rigid bodies.
Well, and one of them, it seemed maybe,
Number 2.
the one, it seemed like I tried doing it as a truss.
Oh.
And it I the very first joint, I came up with answers, but those answers like weren't right. And I don't know if it's because the other.
Let me look at it real quick.
I think it was number 3, yeah, because this is the one I did it as rigid bodies.
Wow, that's going above and beyond, to be honest.
Oh, I was going to ask, in tension and compression, how do we know definitively like which like force vector has the total tension or compression on the end of the member?
Oh, I think you have to rotate it.
Well, you just you find the magnitude, but how do we like discern which force to use? Like when we're doing.
Let me pull it up and you can explain in a little more
Yeah, sorry,
detail.
when
I'm not
we're-
following.
When we're going from the forces into making our stress tensors.
Yeah, at least what I did is I rotated the coordinate system so it was in line.
Oh, yeah. Just you choose a coordinate system, and the one that I always chose is x-axis along the long axis.
Mm-hmm.
And so then all you ever have is, so you're talking about with trusses and stuff, right?
Yeah.
So all you ever have is an XX component.
Well, yeah, I understand that. I'm just
Okay.
saying, like in number 3, there's like 2 reactions on some of the joints, or 2 sets.
Number
of
3
forces.
Oh,
is the
yeah.
one. This is the
Okay,
one
let's
that
do
I-
number 3.
That I couldn't figure out. Or wait. Oh yeah. 3, it's the
Oh, 3, this one.
that one, yes. I tried doing it as
Yeah, you got to do 2 joints here, I think.
like,
Should we do it?
this-
Let's do it.
Yeah, let's do it. And could you start with the top one? Because that's
Yeah.
I just want to see where I went wrong.
Oops. Okay, so come down a little. Okay, so I'm going to number these 1, 2, 3, and A, B, C. It's as easy as 1, 2, 3. And so, well,
So yeah, I guess what I'm saying is it seemed deterministic when I did B first. It was like the forces were already solved for.
okay. So free body diagram, we'll start with B. We have 10,000 F1 and F2. No, F3 there. And the angles, so 40, so each of these is 70. And so Newton's second law says 0, negative 10,000 plus negative 0.342 F1, negative 0.940 F1, plus 0.342 F3, negative 0.940 F3 is equal to zeros. And so that says F1 is equal to F3. And then we have this second one that says, so I'll make that my first equation. I'll do it like this in case we're going to go reduce row echelon form. And then the second equation says negative, we can just do this by substitution, I think, pretty easily. So we have F1 is equal to F3. So this one says negative 1.880 F1 is equal to 10,000. And so this says F1 equals F3 is equal to 5319.
Negative.
Yes. And if you look at it, you can tell it's in compression, so that makes sense that those two are in compression. And this third one, member 2, should be in tension. So now I'll go to, I'll isolate A. We have an upward force here. I'll call that N applied to the wheels. We have a 5,000 here. We have a 5319.15 going this way because we calculated its compression. And then we have F2. And so negative 5,000, 0, plus 0, N, plus F2, 0, 1, 2, 3, and then so 5319.15 times
110.
What?
Cosine is it 110 degrees?
Oh, I was just gonna flip it. So I think then this one is negative 1819.15, negative 5,000. And then F2 is equal to oh, 6819.15.
Oh, it does seem to match.
Okay.
I think I was just getting tripped up with it not being aligned. So like the number that I got, like wasn't like when I looked at the key, I'm like, oh, that's not the same number, but it wasn't in the same coordinate system.
Oh, right. Okay.
Also, by the way, your solutions for this assignment do everything as like rigid bodies.
Oh, okay.
So that was also tripping me up. I
Yeah,
totally
seriously.
this way is so much faster.
Yeah, this is the way to do it. Okay, that's good to know. I thought I had changed all those to.
But so
To trust calculations.
as long as all the forces are on the joints, you could have them going every which way.
Right.
As long as they're
Yep.
like determined.
That's right.
So the only unknowns can be the.
To be a truss, there's only two requirements: no weights, and all the loads are applied at the joints. But they can be any direction. Yeah.
Oh, so we can only do this if it meets the
Yeah.
requirements to be a truck.
Right. So if I said, okay, each of these weighs 4 ounces, you can't do this calculation. I mean, obviously the truss calculation is a very good approximation of that, but including weights means you have to do it as rigid bodies
Okay.
because you go from 2 force bodies to 3 force bodies.
Got it. Thanks.
Yeah. Any other homework questions? Okay, so we're talking about pressure vessels. Last time we did spherical ones, this time cylindrical. And they have to be a lot longer than the radius. The ends can be whatever you want. We're assuming that they're long enough that we're just ignoring what's happening at the end. So you could have one end like this, one end. Oh my God, that's obscene. I'm changing that picture. Okay, I'm making the ends like this for aesthetic reasons. Okay, so let's choose a point. So there's the point we're going to analyze. And think about a line that goes through it like this. And a coordinate system with the z-axis normal to the surface. Like that.
That's a point. Is that along the center? Did you say? It's along like the edge.
The line?
Yeah.
Yeah. So I'm just trying to draw it so that x and y are tangent. That's like a tangent plane to the point, at the point, and z is outward normal. And when we did the sphere, no matter how you sliced it, we sliced it, whatever point you chose, we sliced it exactly as a hemisphere. And we got the same answers in every direction. But this time, we're going to get different answers whether we slice it this way or this way. Okay, so the green and blue are two like fundamentally different ways to slice it. So with spherical, there was only one way. Okay, so first I'm going to go, do I have a name for this? So first I'll just do that blue slice. And if you do a cut like that, you get something like this, where the adjacent material is applying a pulling force. And the adjacent fluid under pressure is applying an inward force. So the green is the fluid, the red is the material. And again, we're going to balance these two forces. So for the material, we have that. Now, this is an XX stress, the way I have this coordinate system drawn. Okay, so we have the XX normal stress times the area of the material is equal to that XX stress. And what can we say about the area of material there? Again, we can do that thing where we like take that ring, detach the two ends, stretch it out, and calculate the area of that rectangle. That's going to come up 50 times in your education classes, that trick for an infinitesimally thin ring for calculating the area. So remember that. But so we have 2 pi r times the thickness. And so 2 pi r thickness sigma. That's the total force applied by the material. And then the force applied by the fluid. We have the pressure times the area. And the area there is pi r squared. We keep using the fact that the walls are thin to sort of fudge these areas and stuff. So pi r squared times p. And now we'll set these two equal to each other. And so we got 2 pi r t sigma is equal to pi r squared times the pressure. The pi's cancel, the r's cancel, and you get that sigma is equal to pressure times the radius over 2 times the thickness.
Look at that.
And that's the same formula we got for the sphere, right? The other way of doing it is where we're going to get a different one. But now we're going to do the green slice. So this time, we're going to have material, and I'm leaving off the ends because we're going to ignore what's happening at the ends. But you can imagine, you know, we're just looking at kind of like a middle piece here.
So it's just like we're taking a slice, like we're chopping off both of like the hemispheres and just leaving a thin piece in the middle.
So what we're doing is we're assuming that this is long enough that the stuff that happens on the, let me complete this drawing, and so we're still assuming that we're including these ends.
Oh, I see. This
Whatever the
is
ends
like
look
a-
like.
Like a tank or something.
Yeah. But we're assuming that it's long enough that we can just ignore this stuff. So,
Next to Mr. Finant. Same.
oh yeah. I mean, this is even more extreme than that because this isn't even an equipolant system. We're just saying we have, like, you can imagine if you have an infinite tube with these finite end pieces, then you can ignore what's happening at the end pieces. And we're just assuming that the tube is a lot longer than so we're ignoring the ends. And we're still going to have the red. I have a lot more arrows I have to draw here. So the red is the material. And then the green is the pressure, the fluid. And again, let's think about the forces, the total forces. So for the material, we have the tension, the tensile stress, I should say, and then times the areas of those two long, skinny rectangles. And so that is, so 2 times the length times the thickness. And then for the fluid, we have the pressure times the area of the fluid, which is 2 times the radius times the length. The 2 times the radius is because the height of that rectangle, is a diameter, not a radius. Okay, and so now we'll set these equal to each other. And the 2's cancel, and the L's cancel, and this time you get that tensile stress is equal to PR over 1T. Okay, so that means that the principal stress tensor in a coordinate system like this is equal to PR over 2T for the XX normal, 0, 0, then 0 PR over T, 0, and then zeros. And so this time, the maximum shear stress is PR over T minus 0 divided by 2. And that is PR over 2T. So this time you get a bigger maximum shear stress than you did for the spherical pressure vessel. Twice as big.
So does that mean that, I guess in reality, it's always somewhere between like PR over T and half of PR over T? I don't know, it seems like if it's a sphere, it's over 2T, right? And if it's infinitely long, it's over 1T. So
Oh.
like the shorter.
Oh yeah, that's a good question. That's a good question. Well, I think the thing is, if the reason that we are assuming it's infinitely long is because things get complicated, not just bigger or small or whatever. They get more complicated when you include the end pieces. Things just don't stay as simple, you know. So I think you probably can't say that. It depends on what the end pieces are like. That's probably true in the way I drew it with spherical end pieces. That seems like a good intuition. That's probably right, but not generally speaking, you know. Yeah.
How come the ZZ isn't also PRT over T?
Yeah.
Because you could slice it like vertically, just like you slice it horizontally, right?
Right. So, okay, so what we're doing kind of is like, so, from like a certain view, we're looking at it like this, where this is just in tension, and then you have the pressure pushing up like this. So remember that for something to be, okay, so yeah, could we calculate something like, so for one thing, remember that this doesn't look like something that you could convert to a stress cube, you know? Remember, a stress cube has to have equal and opposite forces on the two sides. So there's something different going on here, you know? And then, yeah, could we do another cut of this? So we could look at that Z. I don't know. I have to think about that. I mean, the answer is, just because I know smarter people than me have thought about it, is that this pressure pushing up from below is totally counteracted by the tension of the surrounding material. Okay, so I know that that's the case, but I can't really, at least right now, I can't give you an argument of why that's true. Any other questions? Okay, so the next thing we're going to talk about, and we're going to take a while on this. Next overall topic is stresses in beams. And so, for example, if we have a beam like this, can you calculate the stresses at different points on that beam? And this looks like something we did in statics. So what we're trying to do is for a chosen point in this beam, calculate the stress tensor. In statics, we calculated internal loads at every horizontal location along the beam. So that's certainly similar to what we're doing here. But what additional information can we get from stresses? What those internal loads miss are first, they don't take beam geometry into account. So for example, if the cross section of this beam is getting thicker as you move from left to right, the internal loads calculations don't take that into account, but clearly that's going to affect how likely this material is to break at what location. Okay, so stresses will take that into account. So that's important. And then the second thing is internal loads don't distinguish between different points on the same cross section. And so it turns out that even if this thing had a uniform cross section the whole way along it, if you look at look at one single cross section, like look at that spot right there, I tried to make that 3D and it didn't work. But look at this horizontal location, okay? What you have there is some kind of rectangle, or, like if you look at it from the other view. And in that cross section, you have points of high stresses and points of low stresses, and internal loads just says we're at that red line. You know what I mean?
There would also be a point of like no stress? As opposed to
Not always, but in many cases we'll see that. Yes, that's right. So calculating the stress tensors will allow both of these. And we're going to start this analysis with internal loads. And if you took statics from me, you already did that. But we're gonna do it again. We're gonna talk about internal loads again. It's always nice to get a reminder for one thing. We're also gonna include a new type of internal load that we didn't see before. That's torsion of the beam, like a twisting of the beam. And so we're kind of gonna start over at the beginning. We'll maybe go through it a little quicker than we did in statics, but that's what we're gonna do for the next, day or two, is just talk about internal loads calculations. Let's stop there, and on Wednesday, we'll just get into internal loads. Okay.